we will now be looking at the posterior pituitary. Pick this pen. Okay. The posterior pituitary. And specifically the hormones it's responsible for producing. So we have the anterior pituitary in the front and the pituitary in the back. They're like two bulbs. So the structure implies, like this is just like a reversed image. This anterior actually means the front, posterior is in the back. So what's actually happening is, like this image implies, it's a lot more complex. We've got cells and we've got more places where hormones can be produced. Anterior pituitary. So the anterior pituitary, it has a lot more hormones being produced. So it releases more hormones. Whereas the posterior pituitary is more simple, or at least that's what we've researched so far. Right, less research. So going to this image, and I'll send this to be the proof. So let's take it as this. So we've got the posterior pituitary. So treating this as the posterior pituitary, and like saying our brain is the structure, this is the front of the brain, this is the back of the brain, so it calls it posterior pituitary. So the posterior pituitary has less hormones produced from it as opposed to the anterior pituitary. So if this is your anterior and then this is your posterior. The two main hormones it produces are one, vasopressin, also known as anti-diuretic hormone, which goes by ADH. Write that out for you. Anti-diuretic hormone, and also oxytocin. Now, vasopressin, okay, let's take vasopressin one by one. Now, vasopressin literally means vessel pressure. And so what the name implies is, as the name implies, this hormone is responsible for increasing blood pressure, BP. So let's write it out as blood pressure. So there are many components to this, right? First of all, how does it detect? How does system, specifically the endocrine system, detect low blood pressure? Or instead of low blood pressure, I would say detect the need to increase blood pressure. So there are actually two ways that this is done. So we have something called a baroreceptor. Baroreceptor exists on blood vessels. So baroreceptors, which are on blood vessels, and they're essentially receptors that keep a lookout for blood pressure, like literally the pressure of the blood. Is it too high? Is it too low? Now, if a baroreceptor is targeted, we'll actually go to the hypothalamus. So let's say we are in our bloodstream all around the body. Okay, this is your body, very complex bloodstream. And then let's say we've got the hypothalamus, which is kind of like your little computer watching over everything, maintaining, and just making sure. And then hypothalamus will then talk to master gland. Our master gland is our pituitary in whole. Well, specifically the anterior pituitary. But since we're dealing, okay, let's write pituitary. Pituitary. And now I can be talking either to anterior or posterior. So I'll write anterior pituitary, and this is posterior. So what happens is we've got baroreceptors hanging out on blood vessels. Now let's say this is like the little baroreceptor, and this baroreceptor will first detect low blood pressure, and so it will send signal to the hypothalamus that, hey, we have low blood pressure. We need to increase, my bad, I should have wrote send signal. Sends signal, which will basically say, hey, increase blood pressure. Now this will actually trigger the hypothalamus to create vasopressin, also known as ADH. And so, although the vasopressin is a hormone associated with the posterior pituitary, it's actually created in the hypothalamus. After it's created in the hypothalamus, it goes to the posterior pituitary where ADH is stored until needed. So what actually happens is this baroreceptor hanging out on the blood vessels detects low blood pressure and sends a signal to the hypothalamus. The hypothalamus then knows, hey, I need to talk to posterior pituitary to release vasopressin. And the hypothalamus is actually also in charge of creating the vasopressin. So it talks to the posterior pituitary, and then it will take the next step into decreasing the blood pressure. So before we go to how the blood pressure is actually released, let's talk about the second way we detect a need to increase the blood pressure. So one way is through baroreceptors. The other way is actually through osmoreceptors. So another case where we would need to increase our blood pressure is if we have too many osmotes or solutes. Too many osmotes and solutes. And remember, another name for vasopressin is actually ADH. And like we said, ADH stands for antidiuretic hormone. So diuretic alone means urination, so antidiuretic would mean to stop urination hormone. So as the name suggests, that this hormone, what it essentially does is it stops or decreases water output of the kidney, so it kind of takes in water instead of releasing it for excretion, holds in water into our system. And this holding in water will actually increase the blood pressure, because then our blood vessels have like more volume. So if the volume goes up, the pressure should also naturally go up, right? So yeah, kind of back to the osmoreceptors. If we have too many osmoreceptors, too many, say for example, too much salt, we want more water, we want to increase the blood pressure, so we're gonna also activate or send signal for ADH. also goes by vasopressin. And while this one is while vasoreceptors are on blood vessels, osmoreceptors are actually on the hypothalamus. So these osmoreceptors literally sit on the hypothalamus, and they're just kind of sitting out here looking for signals and looking at the bloodstream. Do we got too much solute, too little solute, too much salt? They're very sensitive, and if they pick up an increase in solute, they'll kind of release vasopressin or ADHD, kind of suppress water output, because you want to keep the water to balance the increased solutes we have. And so that's how it works. So these two systems will detect the need to increase blood pressure, 1 and 2. Now, we've kind of touched upon this, but now how do we increase blood pressure? Now, we increase blood pressure by one way, well, a couple of ways. Well, so we said vasopressin also goes by the name ADH, which actually stands for antidiuretic hormone. So antidiuretic means stop urination hormone, stop urine, and this actually translates to like what it's basically trying to do by stopping the urine output is hold water in system. And now holding water in system will increase the volume, which in turn will increase pressure. Will in turn increase pressure. And so as a result, we will have an increase in blood pressure as we need. So that's essentially how vasopressin works to increase blood pressure. And also, again, I've mentioned this, but just to reiterate, the hypothalamus essentially creates the vasopressin and the other hormone, which the posterior pituitary releases. But it's stored here and it's released when needed. And yeah. Now, this is just one hormone, right? So I said the posterior pituitary actually has 2 hormones. Well, at least that's what we know of. ADH, which is vasopressin, or anterior diuretic hormone. And the other one is oxytocin. Now, for oxytocin, there is still a lot of research going into what is oxytocin, what is it involved in, but generally involved in maternal bonding, social skills, and so on. And actually, like specific cases where oxytocin works actually works in a positive feedback loop. With the cervix during birth. To increase like contractions to help the baby come out. So the more contractions, the more oxytocin release, which increase contraction, which keep on happening positively until the baby out. Another one is in lactation, so feeding, milk production. And there's still a lot of research being done into specifically what oxytocin does and other roles of it, but it's been found in autistic children. They have low oxytocin. And although these there has been studies where autistic children were given oxytocin, however, when they were given oxytocin, there wasn't significant improvement, and so it still leaves a lot of questions as to the complexities and like what really goes on in the relationship between oxytocin, being social, maternal bonding, and just autistic kids in general. So to kind of summarize what we went over, so we've got the anterior pituitary, posterior pituitary. Today we focused on the posterior pituitary. So as opposed to the anterior pituitary, the posterior pituitary releases two hormones. These two hormones are actually not created by the posterior pituitary, but the hypothalamus. Hypothalamus stores them in the posterior pituitary. These two hormones are ADH, which also goes by the name Vasopressin. ADH literally stands for antidiuretic hormone. The other hormone we have is oxytocin. Now, oxytocin, there's still a lot of research going on to what it's specifically involved in, its complexities. Generally, we know it's with maternal bonding, labor, and lactation, and it's low in autistic children. Now, antidiuretic hormone, as the name directly suggests, antidiuretic hormones, reduced urination, is how this hormone is essentially responsible for increasing blood pressure, and it does that by suppressing water or decreasing urine output through the kidneys, making sure to keep water in. And so how our body detects the need to release ADH is through two specific receptors called the baroreceptor, which is specifically located on blood vessels. So you can maybe remember that B and B, baroreceptors on blood vessels. Keep a lookout for the actual blood pressure, so VVV. And then we have osmotic receptors specifically on the hypothalamus, which keeps a lookout for solutes. There's too much salt, whatnot, whether we need more volume to kind of balance this out. That's how we kind of maintain our homeostasis.